Well, yesterday we...
Recording in progress.
So yesterday we discussed some basic structures about this extended affine Hecke algebra. And as I said, the main goal of this course is to explain an isomorphism with equivariant K-theory of Steinberg variety. So today I want to start with equivariant K-theory. So I tend to write small and smaller and smaller, so if people in the back cannot read, just tell me, and then I'll try to make it big again. Okay, so if we have a abelian category A, then we can define its Grothendieck group. So it's the Z module freely generated by isomorphism class of objects in your category. So the classes, I will put them in the brackets. And then quotient by the relation that whenever you have a short exact sequence, then you impose the relation that the middle term is the sum of the term on the two sides, okay, m prime and m double prime. Okay. And you can define this also for a triangulated category. Where you replace this condition of short exact sequence by for each distinguished triangle. So for this, for each distinguished triangle, you have a relation like this. Okay, so this is a way to produce from a category Z module, rather an abelian group, which remember the size of your objects. And for our purpose, I will rather consider a vector space, so over C. So we'll be doing the so-called complexified Grothendieck group today. So it means here I take in the C coefficients. Okay, and then the main kinds of category we'll be interested in are the following. So given, let's say, X is an algebraic variety, I will mainly just work with complex algebraic varieties, but the definition is more general than this. It's a finite type. And then you can consider the category of coherent sheaves on X. This is an abelian category, and so we can take its Grothendieck group in the sense I just explained. And this is what we call the K-theory of X. Well, you might have, it's like the algebraic K-theory of X. You might have seen different definitions using like vector bundles instead of coherent sheaves. So this is a version of K homology instead of K cohomology. But anyhow, I will only work with this version in this course. And also, you can observe that this is the same, or naturally isomorphic to the K-theory of its derived category, bounded derived category of coherent sheaves on X. So you just, here, you have a sheaf. You can view it as a complex supported in degree 0, so get an object here, and you have a map. But in the other direction, if here you have a complex of sheaves, you can just taking the alternating sum of the corresponding classes and it's easy to check. This gives you the inverse map. Okay. Okay, and then just some basic properties that will be useful for us. So if you have a morphism between two varieties x, y, and then, so suppose that f is flat, then the pullback is an exact functor. So from coherent sheaf on y to sheaf on x is exact. And therefore, so recall this is given by O. So the f. So how do I write this? So it's Ox cancel with f star Oy at inverse n. Okay. And since it's exact, it sends short exact sequence to short exact sequence, so it gives us a map it induces a map among the K groups, which will still denote by F upper star. Okay. And second, if, let's say, F is a closed embedding, so it's closed embedding. And then assume y is smooth. And then for any, so for, let's see, right, for any m which is a coherent sheaf on y, because y is smooth, it has a free resolution. It has a resolution by locally free sheaves. So M has a finite resolution by locally free sheaves. Let's say such a resolution is I'll denote it by L dot, and this means if you view it as an object in the derived category, it's the same object. And in this case, you can also define the pullback for in this case. So although it's not a flat map, but we can define F upper star from ky to kx just by sending this class M to the pullback of this free resolution. Okay. Okay. And the third thing we will need is that if F is a proper map, then when you take a coherent sheaf on X, and you push forward to Y, the cohomology are still coherent, and so you so we have a well-defined functor from this to bounded derived category of coherent sheaves on Y. And therefore, it induces also a map on the Grodini group just by sending a class M to the alternating sum of its cohomologies. Okay. Okay, and then we will need. Sorry?
What else if F is not proper?
If F is not proper, then this may not be coherent. And also this may not be finite.
Okay.
So then another thing I will need is the tensor product. So we'll restrict ourselves to the case where X is smooth. And then we have the diagonal embedding from X to 2 copies of X. This is closed embedding into a smooth variety. So I'm in the situation of 2, and so I can talk about a tensor product of 2 coherent sheaves on X, and this is defined as the pullback of Okay, these are the operations I will need for what I'm going to talk about. And what I also need is here everything can be made equivariant. So if we started from a connected reductive group acting on an algebra variety X, then we can talk about G equivariant coherent sheaves on X. Okay, so by definition, when you have such an action, you have 2 morphisms. So you have 2 morphisms from G cross X to X. The first one is just given by the action. So A sends GX to GX on X. And the second is just projection. So it just sends such a pair to X. Okay, and what is a G equivariant coherent sheaf on X? It is, by definition, a pair of data. So first of all, you have a coherent sheaf F on X, which is equipped with an isomorphism between the pullback by A and the pullback by P. Okay, so this is an additional data which satisfy compatibility with group action. Meaning that if you do additional product, then you have several ways to first act by this and then act by this, or you first multiply and then pull back, and all this should be, so all this morphism should be compatible with these operations. Okay, so yeah, maybe just to get an idea, a good example to think is, for example, when X is a point, then a coherent sheaf on a point. Yeah, okay, I will try. Thanks. So then call X is just a finite dimensional vector space. And then in this case, call G of a point is nothing but a vector space equipped with a G action. Okay, so that's a representation of, the same as representation of G. Okay. All right, and so everything I defined above, you can consider the equivariant version. So this is a billion category, so you can consider the G equivariant K group on X, and by taking the Grothendieck group of this category, and then you can consider morphisms which are like G equivariant. And then all I said here is still holds. You need some work to show that they still holds. For example, here you need to show that there exists some G equivariant locally free resolution, but it's true. Okay, so what do we want to do with this K-theory? So we discussed about convolution algebras yesterday, and today we're going to do it again, but on the K-theory. So we place ourselves in the following setting. So I want to discuss about convolution algebras. So assume, I will first do the non-equivariant version and then do equivariant later. So assume you are given 3 smooth and proper algebra varieties. And then you have just the product of 3, and you have 3 kinds of projections. So to the first two factor, to the first and the third, and then to the last 2 copies. And let's just denote this projection map by P12, P23, and P13. And then using the morphism we have, the kind of operation we have defined, we can get a map from the K-theory of x1 times x2 times K-theory of x2 times x3 to the K-theory of x1 times x3. Simply by, so I take a coherent sheaf here, let's call it M. So I have a class of M here, and then I have a class M prime here. So since I assumed that these varieties are smooth, so all my 3 map are, so I can do pullback, they're flat, so I can do pullback with them. So the pullback by P12 of M and P23 of N prime. This is well defined. And then here it's a smooth variety, and I can do tensor product. So I do tensor product on x1, x2, x3. And since x2 is proper, so P13 is proper, I can push forward. So I do P13 push forward of this. And this operation is well defined, so I take the class of this. This will be denoted as M convolve with M prime. Okay. So this operation is associative. So this is that means if you have a 4th copy x4, and then you can continue to convolve. You can first convolve these 2 and convolve with some M double prime, and then it satisfies the associativity as you imagine. So I want to point out this procedure is completely general for whichever sheaf theory, or just take functions when you can define pullback and push forward. Then this makes sense. Yesterday, we were mainly doing this for just locally constant functions on this. So maybe exercise. It'd be nice to observe yesterday's situation is, so yesterday, for example, we were doing B quotient by G quotient by B. But this, this is the same as G quotient by B. You take 2 copies of G quotient by B, but then quotient by the diagonal action of G. And then you are in a situation like this where all the xi's are just G mod B. And you can perform you can check that the convolution algebra we defined today is exactly the same as the one we had yesterday. Okay. So with this formalism, you see that some important cases which we'll be interested in, important cases. So first of all, you can take x1 equals to x2 equals x3 equals to x. Then you just get an algebra structure on A equals to the K-theory of the product. Okay. And second, you can take x1 and equals x2 equals x, and then you take x3 is equals to another variety, x prime. Then you look at this. This will tell you that you have let's say A is this, so you get an A module structure on the K-theory of x prime. X times x prime. Okay? So it's just to show you that not only this defines you an algebra, but there's also some natural modules coming in this picture. Okay. And now, of course, when you have G actions on the variety, and you can make everything G equivariant, so everything works in the G equivariant setting. All right, so now what is the situation we'll be interested in? It is the following. So, yeah, so like life is too good to be true if you only consider smooth projective varieties all the time. Sometimes you have some singular varieties, you want to study them and deal with them. That will be our situation. And so our case of interest is the following situation. So situation where you have a smooth variety, you rather have a map from x to y, which is proper. And x itself, it's smooth. But it may not be proper. Okay, so just as for people who know, it's just like so later on we'll be doing cotangent of the flag variety mapping to nilpotent cone. This is such a map, but if this doesn't mean anything for you at the moment, I will explain it later. Okay, so don't worry. So if we're in such a situation, then we will consider Z, which is just the fiber product of X with itself over Y. Okay? So this thing in general has no reason to be smooth, but it sits inside this smooth variety X times X. Okay? Okay, now you look at our diagram here, and you have so you have a copy of Z staying here, and so you have closed variety Z staying here. The first exercise is to observe that. So if you restrict the P13 map to the pre-image of Z by P12 intersection the pre-image of P23, then first of all, this lands again in Z. Okay, this is just by definition of this fiber product. If you write it out, and then you will see this. And moreover, when you restrict to this map is proper. Okay. this follows from, like, you need to analyze this fiber, and this follows from the properness of the map pi. Yeah, I take them all be x, and then I take z like this. Okay. So, so therefore, if you start with sheaves which support, so we can identify coherent sheaves just by push forward. We can identify coherent sheaves on Z as coherent sheaves. Well, at least at the level of K groups. So the push forward of coherent sheaves on Z is the same as the K-theory of coherent sheaves on X, but supported on Z. Okay, and now if you pull back sheaf, which were originally supported on Z, you pull back and do the tensor product, it was supported on the intersection. And therefore, you can still push forward these sheaves. It's still well defined. Okay, because this map is proper. So all in all, this says that this convolution product, so convolution product, still well defined. On KZ, when you view it in this way. Okay, the whole point is the push forward is well defined, and so this formula makes sense, and so you can do this. But as we were doing, we'll do some computation later on, and you will notice that this product, it depends on this embedding of Z into X times X. It's not something intrinsic to Z, and so we'll discuss this later. Oh yeah, thank you. Yes. Okay. And moreover, so this kind of thing will be the algebra we're interested in, and you can also observe that typically, if for any subscheme y prime inside y, then by this thing here, we get an action of a k of z on k of, you do the fiber product of x with y prime over y. Okay, and so this is just the pre-image of y prime. So you get naturally modules for these algebra by taking the K-theory of the pre-image of this of some subvarieties in y. Okay. Okay. And then, as I said, you can add G equivariance everywhere and consider equivariant version of this construction. Okay, any questions? And now I want to further specialize, so specialize to a case where we'll be interested in is the following thing. So you start with a reductive group, G, acting on vector space V. Or just G representation, finite dimensional vector space. And then suppose you're given a parabolic subgroup in G. And it stabilizes a subspace inside V. So subspace, which is P stable. Okay. And now you can do the following. So first you can do a product of G with V0 over P. Okay. Where this quotient is diagonal, you identify elements of this form. And then because your group acts on the entire vector space, just by action, you have a map like this. And this map, I will call it pi. So this map is nothing but just GV0 sends to G acting on V0. Okay. So this is a vector bundle over G mod P, which is a homogeneous variety, and so it's smooth. So this will be my X. This is smooth. And the fiber of this map are just identified with subschemes, closed subschemes inside G mod P, which is a complete variety. So this map is proper. So pi is proper. And so we are in the situation of that kind of morphism. Okay, and so this will be the kind of morphism we're interested in. Moreover, so here I have some group action. So first of all, I have just here G acts by left multiplication, and here G acts because it's a representation, and pi is G equivariant. Second, on this vector space, I have just a natural dilation action. The vector space. So I have a C star action just by acts by dilation on V. Okay. And so here it acts on V0, here it acts on V, and so this map is again equivariant with respect to the C star action. And so at the end I got the map which is equivariant with respect to this group. And this will be the kind of spaces we'll be playing all the time in the rest of this lecture. So let me give it a name. I will just put a bold G to write this product group. Okay. Okay, and so you can consider convolution algebra in this generality. And for our purpose, we're interested in affine Hecke algebra. And in that situation, what do? You consider G action on its Lie algebra. Well, by the way, I have assumed my G is over C. So on its Lie algebra by a joint action. Okay. And then here I have a fixed Borel algebra as yesterday. And it acts on the Lie algebra of itself, and in particular, this action preserves the radical of its Lie algebra. Okay. Okay, and then you just do the construction above. So we have this maps to G. And so this map is a famous map in representation theory. So it's not hard to see that using Keeling form, this is identified with G dual. And under that identification, this is identified with the cotangent of the flag variety G mod B. Okay. And this is actually the moment map for the G action on this cotangent space. But we don't need all of that. So all we need to know is that this is a particular case of that above statement. And we can define a convolution algebra using this. And so more particularly from now on, V will be the so-called, this was Z in from now, yeah, maybe let me fix some notation. So I write flag to be G mod B. This is flag variety, and then from now on, this will be T star of flag times T star of flag over actually so over the nilpotent cone. So you notice that all the elements here arrives in the set of nilpotent elements inside G, and then I will do this. So this is the so-called Steinberg variety. And by this general formalism I have explained, we now know that its equivariant K-theory comes with an algebra structure. N is the set of nilpotent elements in G. So this is it is not so important for our purpose. You can do it over G. Okay. So the theorem of Kazhdan-Lusztig and also partly due to Ginzburg is that we have the following isomorphism. So remember yesterday we defined this extended affine Hecke algebra. And as I said, its definition depends on a group G. Okay? Now we define this, we consider this for the group which is Langlands dual of G. Okay? So just in practice, you replace all the co-characters by the characters of G. And the statement is this is isomorphic as an algebra to this equivariant K-theory of this Steinberg variety. But this is for G. Okay, the point is that there's a Langlands duality involved. So here, if you take this coherent side, you work with G, and then you should work with the G check on the affine Hecke algebra side. Okay. So this is I want to try to explain the proof for this theorem. And this is what I meant by geometric realization of affine Hecke algebras in the title of these lectures. But before going on, I want to make a remark that actually in geometric representation theory, there's a full variety of Hecke algebras which can be realized in this way just by choosing that G, V, P, and V0 carefully. So, so first there is, and also, so there's a similar version using, first of all, Borel-Moore homology instead of K-theory. And there you get a so-called degenerate affine Hecke algebra. And then there's also a version where you started with some quiver representation. So quiver representation, where you have some quiver, and then you have some dimension vectors at each of the vertices, and then you can consider the group which is the product of GL of VI acting on representation of this quiver with the corresponding dimension vector. And then you can play a similar game by taking a Borel, and you get a convolution algebra. You compute it. This is you get something called quiver Hecke algebra, or people also call it KLR algebras. So this is, I think this is still Kazhdan-Lusztig. This is Varanullo-Westrow. and Rouquier. And then you can also do the kind of situation where, let's say, K is the field of Laurent series, and then let's say O is the integers. And then if you're given a group G acting on a representation V, you will get naturally an action of GK on VK, and such that the parabolic subgroup GO acts on V of O. Okay, so everything is a bit infinite here, but you can reduce to finite cases, and all this kind of thing still work. And if you start from this as the setting over there and consider the corresponding convolution algebra, you will get, so in this case, you get K of some Z attached to these data. I don't know how to write it, GK, VK. So in this case, this algebra is actually commutative for some miraculous reasons, similar as in geometric Hecke. And Braverman and Finkelberg how do we spell Finkelberg? And Nakajima used this to define a Coulomb branch. So Coulomb branch, or rather K-theoretic Coulomb branch, is equal to the spectrum of this commutative ring. Okay. So I mentioned this just in case you meet them someday, then you know that they are just the kind of convolution algebras we have been discussing today. Okay.
It's a finite type?
This ring, yes, this ring, it's a finite type over C. Although the space are like int, etc., but at the end you get an algebra which is finite type over C. So yeah, it's a bit tricky. You need to, let's see. In the it's a good question, I forget. Yeah. Sorry. Okay, so all right. So that's a side remark, and then let's try to see how does this isomorphism work. In this case, what you do is something like so you fix a Borel, and then in G mod B you have a flag, and you look at only representations which preserving that flag. It's like here you can reinterpret this as a space of, so you have, yeah, maybe I should write it here. So this G and can be identified with pairs of elements. So we know the flag variety is all the Borel subalgebras in. So let's say Borel subalgebra in G, and then this can identify with the pairs and X and let's say a Borel. I would write B prime to distinguish with this B, and then the condition is X belongs to the radical of B prime. if we write it in terms of, for GLN, this identify with the flag of vector spaces in Cn. And then this is just, you have a flag, and you have a linear endomorphism which preserve that flag. And in the quiver case, you can talk about the same thing. Yeah. Okay. All right, so we're in business now. So we want to compute some equivariant K-theory. Let's start with the most simple case. So what is the kg of a point? So kg of a point, as I mentioned already, so coherent sheaf, G equivalent coherent sheaf on a point, this is nothing but representation of G. Okay, so this is just the Grothendieck group of representation of G. And now let's start with some easy case. So if G is just one-dimensional torus, C star, then in your opinion, what is huh? The integers? Not quite. I have to have a, I mean, it's close. You mean integers character of C star, but then, yeah, so, but then you have some tensor structure. So you have, so, okay, so what is, maybe, let me say, well, in a sense it's correct. So let's say what is representation of C star? It's a graded vector space. So this is graded vector spaces. And therefore, so to remember the size of an object, you just need to remember its graded dimension. And so K C star a point is the ring of Laurent polynomials in one variable, where you just send a graded vector space V. So graded vector space is sum of Vi, I, and integer, and then this is sent to sum of dimension Vi times x to the power of I. Okay? So, okay, it's a good start. And now we will have a torus of higher rank. Of rank, let's say rank R. Then you can imagine that the equivariant K-theory is just a ring with with R variables. Okay. Okay. And now, if you have a representation, so we fix, let's say T is the maximal torus in G, and let's say we're considering complex representations of G, and you know that for a representation of G, it's enough to determine its character. In other words, it's enough to remember how it is as a T module. Okay, so through this forget map, you have a map from Kg to KT, bad notation, G of a point, to kt of a point. And well, if we don't fix a basis, then it is more natural. It is more natural to write this as like e to the power of lambda, for lambda which is a character of T. Okay, and then we denote this ring by RT, so character ring of T. So and then by the vowel character formula of G representations, you know that the characters for representation of G give you W invariant elements in the character of T. Okay, so using vowel character formula, you can show that kg of a point is RT invariant by the finite vowel group for its actual natural action on the character of Taurus. Okay. So below I will write this ring as RG, and we have something like this. Any questions? Okay. All right. So we have the case of a point, and next we have an induction formula on equivariant K-theory. So if you have a subgroup in G, H, and you have a variety with H action on X, and then you can consider the induced variety, which is G times X over H, which is still the same kinds of quotient as we explained just now. And you can consider, on one hand, you can consider coherent G equivariant coherent sheaves on this variety for the left G action. And on the other hand, you can consider H equivariant coherent sheaves on X. And I claim this is an equivalence of category. Okay. So if you have a coherent sheaves on X, which is H equivariant, you should roughly imagine as a space over X equipped with an action of H. And then you get by induction the only way you get a G equivariant coherent sheaves whose restriction to X is by inducing with the G action. And so you get a map in this way, and this is and if you have a coherent sheaf here, you can restrict to X, and it gives you the quasi-inverse of this functor. And this provides you an equivalence of categories. So this tells us that the G equivariant K-theory of this induced variety is the same as is naturally isomorphic to the H equivariant K-theory of X. Okay, so in particular, now take X to be a point, and if you want to compute G equivariant K-theory of the homogeneous space G quotient by H, then this is the same as H equivariant K-theory of a point, which is the character ring of H. Okay. All right. Which board is the second board? A. And another fact we will use very often is the so-called dévissage. So if you're in a situation where you have a closed embedding of x into y, and then an open embedding from u to y, so this is open, this is closed, then the open embedding is flat, so you have a pullback from ky to k of u, and this is actually surjective. And then you can push forward, so this is j upper star, and then you can push forward through this closed immersion and get k of x. And usually you should get a long exact sequence. With here you have some higher k group. So all the k I've been discussing is really like k0 of an abelian category. And then you here normally you should get some k1 of coherent sheaves, the category of coherent sheaves on U. And then there's a long exact sequence which continues. But later for us, when we're analyzing this K-theory of the Steinberg variety, whenever we use this, actually the K1 will be trivial, and so we get a short exact sequence. But we'll come to this later. So, okay, so this is Davy-Sach, and then another important thing we'll use is the so-called Thom isomorphism. So this says if you have for any G equivariant vector bundle, let's say pi from V to X, and let's write I for zero section of this bundle. And then the theorem says the pullback by pi yields isomorphism between the equivariant K-theory of X and the equivariant K-theory of V. Okay? With an inverse given by I upper star.
Okay, so regarding the Davy-Sach, I think the K1 is not going to be trivial. It's just that the long exact sequence
it's not going to be trivial in general, but we will be dealing with some very particular space. I will discuss about them, and so I will only use the case where K1 is trivial. I'm not saying.
I think the K1 is not trivial. You will have like C star in the K1, but the long exact for the particle spaces.
Yes.
With affine gradients, the particular reason is that this long exact sequence splits off into short exact sequences degree wise. But I think the higher ones are also not trivial. It's that they just don't contribute to K0.
Ah. Okay. You need to teach me about this. I don't know this very well. Okay. So so I will not give a proof of this theorem, but just to convince yourself, you think about the case where X is a point, then a vector bundle is just a vector space. And what is the K-theory of a vector space? Well, what you know is that the only projective module for a vector space is just the free module. And so all the coherent sheaves have a finite resolution by free module. So it's at the end, your K-theory only have one object in it, and it's the same as K-theory of X. And you need more argument to make that, to make an argument for this proof. But we will discuss, we will need how this I upper star and I lower star looks like. And so for example, for computing I push forward, of the structure sheaf, on X, you will need to take some sorts of resolution, and then this is, well, naturally you will just take the Koszul resolution. So how does it look like? You start with the push forward of OX, and then you resolve it by OV times the just the wedge product of V dual, and then you as a vector bundle, and then you pull back to yeah, maybe I should write it like this. So take pi push forward of, and then you continue. Okay. So right, and so using this resolution, you can show that I lower star, the class of I lower star in OX is the same as the alternating sum of this context. So 0 to dimension of V, so -1 to the power of 0, and then you take the class of lambda I of V. Yes, because right. So yes, I think this is correct. Or maybe I should put a pi star. Yeah, sorry, got confused. Yeah, I should put pi star of this, of course. And then right, and then so. Right, so then if I take I upper star of I lower star of this OX, so I upper star is inverse to pi upper star, so this will just be the sum of I equals to 0 dimension V of lambda I of V. Okay. So this is the Euler class of this vector bundle. We will denote this by lambda V later on, and this will be frequently used. Okay. So in particular from this, you also obtain that for any f in Kg of X, if you do I upper star, I lower star of f, you just get lambda V times f. Okay, and this can be generalized. I think I forgot V check as I went on. So huh?
Why is there a zero section?
It's a vector bundle.
But it's not the code.
Okay. Well, more generally, if you have just a, or let's say more generally, given a closed embedding, let's say make everything G equivariant embedding, such that N and M are both smooth. Then, well, you could imagine around the neighborhood of N in M, this map looks like you take the you take the normal directions to n, and then you have a vector bundle like this, and then this is like a zero section of this bundle, and so therefore, if f is in G-equivariant K-theory of n, then I push forward of f and then pull back. This is, you take this Euler class lambda of the conormal of n in m times f. Okay, so this is something which is useful for us. And finally, we have a kind of a reduction. So you see, in a sense, I at the first place, I'm interested in K-theory of cotangent of G mod B. And using Tom isomorphism, I would reduce to computing just G-equivariant K-theory of G mod B. And using this, that is the character ring for B. So, and the character for B and the character for T is the same. So all these computations tells us that, so now we can understand what is K of G equivariant. So I put my bold G, but it doesn't matter so much. So T star of G of the flag variety. So this is a vector bundle over flag variety. So by Tom isomorphism, this is the same as G equivariant K-theory of the flag variety, but flag variety is just G mod B. And so by induction, this is the same as, so B times my C star action, equivariant K-theory of a point. But for B representations, it has the same simple objects as T representations. You just get non-trivial extensions. But when you go to the K group, you forget about the extensions. You only remember the size of your modules. So actually, this is the same as K T times C star. Okay, and so this is our, so this group I will denote it by both T, and this is our RT. Okay, and now, as I said, K of C star is just a Laurent polynomial ring with one variable, and we have a particular C star here. Let's write this as C, Q, and Q inverse. And then, what is this? This is C of Q, Q inverse. And then it's functions on the characters of this maximal torus T, which is X check for the dual torus T check. And we're approaching where we were yesterday. All right, so what we want to prove? We want to prove our Hecke extended affine Hecke algebra is isomorphic to this equivariant K-theory. Now, let's take a minute and try to remember what we had yesterday. So yesterday we said by Bunchton presentation, this algebra is generated by Ts and X lambda. So now I'm doing everything for G check, so I'll switch notations. So here S is a finite reflection, and then lambda is in co-character of T check. So this is, so let's write this as X, okay? And then they subject to some relations, which we have written down yesterday. I'll not copy them. And then there's one thing I didn't have time to say yesterday, but it's kind of important, is that this algebra has a polynomial representation. So what is a polynomial representation? I'll denote just by pole. This as a space is nothing else than this thing. So it's just RT. So it's C of Q plus minus with with E lambda, with lambda in X. And we want to have an action of the extended affine Hecke algebra on this polynomial ring. So yeah, it's like endomorphism over this ring. And let me write rho for this action, and I write an A for algebraic, as we will have a geometric action later on. To define such a map, you just need to describe the image of the generators and check they satisfy the relations. And so the x lambda will just x by multiplication by E lambda. Okay, they naturally commute, and then over this commutative set algebra, this is totally fine. And then the T, so we have some Ts for each of the finite reflections. Let's write our S as alpha. So, so we need to say how it acts on these generators. Then it acts by sending, maybe I will just write Ts alpha acting on E mu. This is given by Q times E to the power of S alpha mu plus Q minus 1 times E mu minus E S alpha mu divided by 1 minus E minus alpha check. Okay? For all the mu belongs to X. Okay. It's an easy exercise, just using the relations I've written on yesterday to check this is well defined. Okay? And so this is the endomorphism ring of polynomial of this vector space or the CQ module. Just to say this is a representation of this algebra. Yeah. Okay. I will come back to this later. It is. There's an interesting exercise. I'll still write it down because I think this is kind of important. So the point of this exercise is to show polynomial representation is a spherical representation. So we remember that the finite Hecke algebra is a deformation of the group algebra for the finite vowel group. So in particular, you can consider the analog of idempotent for the trivial representation. And in this case, so you just can take you take the sum of all the elements in the finite vowel group. You get this. And first, you check that, that if you do Tx times E, this will be equal to Q to the power of the length of X times E, and it equals E of Tx for all X in the finite vowel group. Okay, and therefore this tells you that using this you can show that. So this is a particular element in the extended affine Hecke algebra, and so you can consider the left module, which is just given by right multiplication by this element E. Okay? And this is this is isomorphic as the induced module from the sub-algebra, which is the finite Hecke algebra. And you define a character of this algebra on C of Q inverse, where where this action is given by HF. So this is action by morphism epsilon, and epsilon is defined by sending an element Tx to Q to the power of Lx, the length of x. You check this is well defined. It gives a well-defined character on HF, and therefore you have the induced module, and then you check these two are isomorphic as module. And from this, you can see as a size, this space have the same size as the polynomial representation, because the affine Hecke algebra has a basis given by x lambda, like the Laurent polynomials in x lambda, and then times the TW for W in a finite vowel group. And then in this procedure, you have killed all the TWs, and so as a space, it's the same as a polynomial representation. And moreover, they're actually isomorphic as representation. So you can show that Hx times E is isomorphic to the polynomial representation defined in this way as Hx times modulus. Okay. Okay. All right. So we have the polynomial representation, and I recall that when we were discussing this convolution algebras, I explained that when you have a map like pi from x to y, and then we have this equivariant K-theory of this fiber product defined by, so maybe I write it out, so of this fiber product. But then for any sub-scheme, or actually any morphisms, no, let me be safe. Any subschemes inside Y, this acts on x times y prime. Okay, just by convolution. But now I can just take y prime equals to y, and therefore it always acts here. Okay? And for us, the map we're discussing is the map from T star of flag to Y's nilpotent cone. And here we had our Steinberg variety we're interested in. And here, X is just T star of flag. And we have seen this is the character ring for this RT, which as a vector space is equal to the polynomial representation, just to canonically. Okay, so what do we have now? We have a map from the extended affine Hecke algebra through this algebraic action on endomorphism of the polynomial representation, and then using identify RT with just as a space to polynomial representation. This is the same as endomorphism of Kg of T star of flag. And by convolution, we had an action of the Steinberg variety. So this I write as rho G for geometric. This is actually action given by convolution. Okay. So the first claim is this map is injective. I will prove it later. So yeah, maybe. Now comes the important. Okay, so using that diagram, the proposition we're going to prove is, first of all, rho g is injective. In other words, the geometric representation is faithful. And then, second, the image of rho A is contained in the image of rho g. Okay? So if you know this is injective and the image of this map is contained in the image here, that means you have a map from H extent to this. Okay? So these two things would imply that we have an algebra homomorphism phi from Hx to Kg of Steinberg, making the diagram commute. Okay. All right. So, kind of need to manage my time. Okay, so how do you prove this claim? The first part, let me see how I want to organize. So let's say strategy of proof. So the first part I will prove using localization theorem, which I will talk about it next time. And for the second part, so your Hecke algebra, you know its generators. It's enough to prove the image of the generator is contained in the image of rho g. So enough to show that rho A of x lambda and rho A of Ts belong to image of rho g. Okay, and for this, we will need some maybe let me discuss a little bit the structure of the Steinberg variety, and then we will finish this proof next time. So recall our Steinberg, right? So yeah, I'll use this identification. We identify the cotangent of flag as the space where an element in the flag is just a Borel subalgebra inside G. Let me put Borel prime because I had B for the fixed point, and then an element X such that x belongs to. So I will consistently write n prime to be the radical of b prime. Okay. And now Steinberg variety is 2 copy, and the map to G, if you write it in this way, is just projection on the first coordinate. So this pi is just sending such a pair to x. Okay? Okay, and now if you do the fiber product, using this interpretation, what does it mean? It means that you take an element here, you take an element here, such that the projection to G are the same. So this space consists of following triples. So you have x and b1 and b2, such that b1, b2 are Borel, and then x belongs to the intersection of n1 and n2. Okay? Okay. And so this thing, it just maps to 2 copies of the flag variety, where this is just sent to b1, b2. Okay, but we're considering everything G equivariantly. So you want to know how well, like what our G orbits look like in this space. So on the flag variety, we know that, so G acts diagonally, and then, okay, so we have this isomorphism. I write it out. So the flag is G mod B. For the diagonal action, we have already mentioned this is the same as you induce from the B orbits on G mod B. Okay. So this isomorphism, just by sending G and let's say G prime of B to G B, and then G prime of B. So then the left G action here identified with the diagonal action here. And here we know how the B orbits look like on G mod B. This is the Bruyère decomposition we discussed yesterday. So the B orbit here is indexed by elements in a finite vowel group. And moreover, we know that if you take the closure of such a B orbit, this is the union of all the elements which are smaller than W in the Bruyère order of BV, B over B. Okay, I didn't discuss the Bruyère order, but you can take this as a definition. Okay, so this means the G orbits, the diagonal G orbits here, are also indexed by W. So we will write OW inside 2 copies of flag. The G orbit index corresponding to like G, B, B, W, B over B. Okay, so there is an element here consists of a pair of Borel, and then an element here is so-called a pair of Borel in relative position W. Okay, so this means this is B1. Well, you can take it. This is a definition. Okay. So B1 and B2 in relative position W. Okay, and now you look at your Steinberg variety and you ask, how does it look like? So we have this map P, and let's consider the inverse image of an orbit. Okay. So what does it mean? It means by our description, I have a pair of Borel in relative position W, and then so B1, B2 belongs to OW, and then its fiber at this point is just the intersection of the corresponding Borel. Okay, so so how to say, this is, I think I'll make some mistakes on the signs, but this is more or less the intersection of N1 with, yeah, maybe I just put it as, but in any case, the point, what is the point? The point is over OW, which is a G orbit, this is a vector bundle. Okay, because the structure is transported by G everywhere, so this is a vector bundle. And let's write this as ZW. And you can see that, so and then let's write Z smaller equals to W to be P inverse of the closure of OW, which is a union of orbits smaller or equal to W. So this is nothing but the union of V smaller equals to W of ZV. Okay, and so we have sort of a paving of our variety Z by vector bundles over the orbits. Okay, and then we'll use this next time since time is up. But I want to say a word about the structure of this Z. So if you think about it. So let's take the example of SL2. In SL2, the flag variety identify with the one-dimensional vector space in C2. So this is P1. Okay, and then it has two orbits which identifies with A1 and 0. So let's say this is the identity element, and then this is BSB over B. And you look at what should be the fiber of, yeah, so we can reduce to a, using this we can just reduce to consider, how to say, okay, maybe I do the, so in this we have two orbits. One is the identity. So for the identity, the two Borel are just the same. So this vector bundle over it is just the radical of the Borel. So Z1 over O1 is a vector bundle of rank 1. But if you're over ZS, then two Borel are in relative position S means that they're opposite to each other. So the intersection of their new radical is just 0. Okay, and so therefore over this ZS is just isomorphic to OS. Okay, so you see actually your Steinberg variety is a very singular object. So you have, so basically this picture up to some G equivariance tells you that it's something over P1. And on the, let's say this is P1, and on the open locus it's just P1, but then you add some one-dimensional fiber at the point 0. So this is a picture of your Steinberg variety. Yeah, but right, I think I will stop here today, and then we will analyze more about its equivariant K-theory tomorrow.
Thank you very much, Peng, for this beautiful talk. Are there questions?
Hi, you've, I guess, described like a geometric interpretation of hx. I was wondering if we could do something similar for hf that you defined last time, maybe by like restricting the equivariance or something.
Oh, it is, so HF is a particular case of HX, just by choosing the group to be simply connected. So all what I said is valid for that case.
Okay.
Yeah.
Okay, so thank you.
Other questions?
So I have a question about the polynomial representation.
Mm-hmm.
Is there a nice interpretation of it in terms of a p-adic adductive group when you specialize Q to prime power? Does it come from some kind of, I don't know, universal family of an ramified principal series or something like that?
You need to ask someone in the audience. Nick?
This is for the
Maybe.
Q&A session.
Yeah. Yes.
Other question? Okay, so it's time for lunch. Thank you very much again.